Multi-threading in Python sounds powerful until you discover the shocking truth. Your threads aren't actually running at the same time. The global interpreter lock, the infamous GIL, silently controls everything. If you've ever wondered why Python threads feel slow or fake, this explainer will finally make it all click. For years, developers have heard conflicting advice about Python and multi-threading. Some swear threads make their programs faster, while others insist Python can't do real multi-threading at all. The debate is confusing, but the truth is surprisingly simple. In CPython, the most widely used version of Python, true parallel execution of Python bytecode cannot happen in multiple threads. That doesn't mean threads are useless, but it does mean they don't work the way most beginners expect. Let's break down the mystery, the misconceptions, and what you should use instead. The culprit is the GIL, Global Interpreter Lock. The GIL is a mutex that protects access to Python's internal memory structures. Only one thread can hold the GIL at a time, and only the thread holding the GIL can execute Python instructions. So even if you create 10 threads, only one runs Python code at any moment. The others wait their turn. The GIL constantly switches between threads, which is called context switching. From the outside, it looks like things are running in parallel, but under the hood, it's an illusion, a controlled, serialized dance. To understand the why, go back to Python's original goals: simplicity and memory model safety. Python was designed to be easy and safe. The GIL prevents race conditions in the interpreter's memory management without forcing every developer to worry about thread safety. Python objects are reference counted. The GIL ensures only one thread mutates these counts at a time. Performance, surprisingly, is also a reason. Without the GIL, single-threaded Python programs in CPython would be significantly slower due to all the locking overhead. Python chose simplicity and safety over raw parallelism. Absolutely, threads are not useless. They shine when dealing with I/O bound tasks. During I/O waits, the thread releases the GIL, allowing another thread to run Python code in the meantime. So if your program spends most of its time waiting, Python threads can improve performance drastically. Example tasks that work great with threads include downloading multiple files, sending many HTTP requests, and managing thousands of socket connections. This is where the myth becomes painfully real. If your work is CPU heavy, meaning it involves raw computation, Python threads offer zero speedup. Examples include image processing, number crunching, machine learning loops, data compression, and encryption. Since CPU-bound threads all fight for the GIL, only one can compute at a time. This is why multi-threaded computation in Python is commonly disappointingly slow. Although threads can't achieve real parallelism for CPU tasks, Python offers alternative tools. Multiprocessing launches separate Python processes, each with its own interpreter and its own GIL. This provides true parallel CPU execution, great for heavy computation, with a simple API similar to threading. However, it has higher memory usage and slower data sharing between processes. See extensions like NumberPy and Pandas bypass the GIL by performing computation in optimized C code underneath. NumberPy can use your multi-core CPU even though Python itself cannot. Essentio handles massive I/O concurrency with a single threaded event loop, avoiding GIL contention. It's great for web servers, chat apps, API gateways, and streaming services. Some alternative Python implementations remove or change the GIL, such as PyPy, Python, and IronPython. CPython 3.13 Plus is even experimenting with removing the GIL, but the version everyone uses still includes it today. Use threads when you're doing mostly I/O, your task involves waiting, or your workload is latency sensitive. Avoid threads when you need raw computation, want to maximize CPU usage, or your task is data heavy. Python can do concurrency, but it can't do parallel computation with threads. The GIL is not a bug, it's a design choice. Understanding this saves developers countless hours of frustration and performance confusion. If your program is slow because of the GIL, use multiprocessing, NumberPy, or C-optimized libraries, or Essentio for I/O concurrency, or switch to a GIL-free interpreter. Python's threading model can feel confusing until you understand the GIL and how it governs everything. Once you grasp the difference between I/O bound and CPU bound tasks, Python's behavior finally makes sense. Threads are fantastic for concurrency, processes are fantastic for parallelism, and async is fantastic for massive I/O. And the GIL? It's not your enemy. It's part of Python's DNA. Master these concepts, and you unlock the real power behind Python's concurrency ecosystem.